Hi all, I am Miller Trujillo from Universidad de los Andes at Colombia. This is a collaborative work with Mario Linares Vázquez, Camilo Escobar Velázquez, and Nicolás Cardoso from Universidad de los Andes, and Ivana Dusparik from Trinity College, Dublin. Our work is about neuron coverage as a testing metric for deep reinforcement learning. First, let's start talking about reinforcement learning. So the way it works is that there's an agent that perceives a state from an environment and performs an action that will change this state. Furthermore, the environment will give a reward signal based on the agent decisions. So what we want to do here is to learn to pick an action that maximizes that reward signal and a long-term reward. For this, we could just go further and explore the possible states and the possible results and learn what will happen based on this experience. Then we will take the best actions depending on the state and the experience. Actually, this is called a policy that is a function from states to actions. However, as you can imagine, as the environment gets complex, trying to learn how to pick an action gets harder. Here is when we can introduce neural networks. We can use them to approximate the policy, and this will be really useful as the state space or action space become too large. So deep reinforcement learning is simply using a deep neural network to work as a policy. But the problem using DNNs here is that we actually don't know if the DNN is approximating an optimal policy or even a good one. In contrast to supervised learning, here we don't have an explicit goal value. Our only metric is reward, but it won't tell us if our policy is optimal. And by now, there are no specific testing techniques for DRL systems. So the question is, how do we know that the output from the DNN is the expected one? If we ask this question using purely DNNs, there are some metrics that addresses. For instance, the neuron coverage that is an adaptation of a statement coverage when testing regular software. Actually, neuron coverage had been studied and proposed as a white box metric in some frameworks like DeepXplore. Moreover, there are some testing tools like DeepTest that empirically demonstrates that changes in neuron coverage are correlated with changes in the actions of self-driving cars. But does these traditional DNN testing techniques actually apply to DRL? That is our main question and motivation, but in this work we focus only in neuron coverage. Therefore, our research questions were: is there any difference in the evolution patterns of neuron coverage for the different layers in a DeepRL system? And is there any correlation between neuron coverage and a cumulative reward in a DeepRL system? To address these questions, we designed an empirical study using the mountain car problem, which is a classic control problem where there is a truck stuck between two mountains and we want to climb the right side mountain. However, the engine of the truck is not strong enough, so it have to move back and forth to gain momentum and climb the mountain. So the goal is to climb the mountain, but there is a time limit that is 200 steps. The environment describes the states using the position and the velocity of the truck, and the action that the agent can take are move towards left, move towards right, or simply do nothing. Also, the goal is described in terms of the position, so if the truck reached a position greater or equal to 0.5, then we say that the truck have climbed the mountain, and we will give a positive reward in this state. Otherwise, the reward will be -1. Now, for solving the mountain car problem, we randomly select two models that use DQNs. The first model, Model A, have 4 hidden layers, and the input layer use the current and the last state. The Model B use the current state as an input and have 2 hidden layers. For both models, the output layer is the same as there are only 3 possible actions. It's important to note that in Model A, the second layer is a flattened version of the first layer. That means that the neuron's activation values are the same between these layers. Now, for collecting the data, we train and test the models in sequences of iterations, episodes, and stages. So, we start training performing at most 200 iterations or actions per episode. If during a training episode the truck climbs the mountain, then we perform 20 testing episodes. And this will happen 1,000 times as we use 1,000 training episodes. And also we use 5 stages per model. Understanding an stage like this whole process of training and testing. These were the training parameters that we use for the models. And finally, These are the metrics that we use to address our research questions. The first one is neuron coverage, that is counting which neurons were activated for a specific input. The second one is neuron layer coverage, that is the same from neuron coverage but only counting for a specific layer. These two metrics will help us to understand the relationship between coverage and reward. The third metric is cumulative neuron coverage, that is the total number of neurons that had been activated until a specific time step. And finally, the last metric is cumulative neural layer coverage, that is the same from cumulative coverage, but again for a specific layer. These cumulative metrics will help us to address our research question about the evolution patterns. This is because these metrics take into account previous values, so we can evaluate evolution in a better way. Let's see at this example to better understand our metrics. So let's assume this network, the green neurons mean that were activated at this step. So in the first iteration, we will have 5 neurons activated in the whole network. Therefore, the neuron coverage is 5 out of 12. And if we take a look to a specific layer, for example, first layer, L1, there were 2 neurons activated. So NLC for this layer is 2 out of 5. As there is no previous iterations, in this case, the cumulative metrics have the same values for the non-cumulative. For the second iteration, there is again 5 neurons activated in the whole network. Thus, the neuron coverage is 5 out of 12. However, there are 3 neurons that are active now that were not active in the previous iteration. Therefore, the cumulative neuron coverage is 8 out of 12 at this moment. For the layer level, happens the same. So even though for the first layer there are only 2 neurons active, the cumulative version will count up to 3. Now, after performing the experiments and computing the metrics, we can start talking about the evolution of coverage for Model A. So these plots show the distribution of CNC and CNLC over training and testing in Model A. During training, for CNC, on average, 95% of the neurons were activated, and all the layers were able to execute all of their neurons, that is CNLC. Another interesting thing here is that the output layer of the Model A report the lower average 80% from the two models, showing that having less neurons does not necessarily result in higher cumulative coverage. Now, going to the testing results, we can observe that there is a reduction in the cumulative coverage in the layer and network level. More concretely, the reduction was 45% on the average CNC and 42% on the average CNLC. Finally, during testing, 42% of the episodes succeeded climbing the mountain. There is a success rate of 42%. Now, this plot shows neuron coverage and neuron layer coverage per episode for training in Model A. Note that for visualization purposes, we only present 3 out of the total 5 stages. Well, now we can observe that neuron coverage behavior for the output layer is erratic across the different stages. Also, for the first 2% stages, the first layer shows higher coverage than the following layers. However, the third stage flips such behavior. Again, remember that the second layer is a flattened version of the first layer. So there is an exact mapping between these two layers, and that's the reason because the second layer is not showing in these plots. Now, let's look at the reward. These plots show the cumulative reward per episode. At a first look, the behavior of the signal seems erratic, especially because the best rewards are not necessarily reached at the final episodes. But if we take a better look, we can also observe that these reward signals look quite similar to the coverage signals of the last layer, at least for this model. In contrast to Model A, Model B shows lower average CNC with an 86%, and only the first and the last layer were able to activate all of their neurons. For Model B, the reduction on testing was 30% on average CNC and 25% on average CNLC. Finally, this model got a 77% success rate. Look that even though Model A have better cumulative coverage during training, its success rate and cumulative coverage in testing are lower compared to Model B results. For this plot, the behavior is similar to the one described at Model A. The last layer is erratic and the first layer shows higher coverage than the following layers. And also, looking at the cumulative reward, we can observe that the signals look similar to the coverage signals at the last layer for this model too. After noticing this behavior, we decide to compute Pearson and Spearman correlations to evaluate this. However, the result was negative or lack of correlation. Now, given our results, we found that better coverage in training does not necessarily mean better coverage in testing. Also, that training and testing evolution patterns are not necessarily the same. And because of the negative and lack of correlation between coverage and reward, we think that neuron coverage is not sufficient to reach substantial conclusions about DeepRL systems. Finally, as future work, we think that neuron coverage as a testing metric should be extended to other DeepRL scenarios, like other classic control problems, to consolidate the validity of our results. And also, similar approaches could be used to evaluate other DNN-based models. Before closing the presentation, I would like to make a quick summary. As said before, our goal is to see if traditional DNN testing techniques apply to DRL, and we focus in neuron coverage. This is to present a first step towards testing of DRL systems. In this case, we try to answer these two questions. The first one about evolution patterns of neuron coverage, and the second one about correlation between neuron coverage and cumulative reward. For addressing the previous questions, we conduct an empirical study using a classic control problem, mountain car, and randomly select two models from GitHub that solve it. We also define these four metrics based on neuron coverage and cumulative neuron coverage, which have network and layer level. And finally, we obtain some important insights like better coverage in training does not necessarily mean better coverage in testing. Also, that the evolution patterns are not the same between training and testing. And because we cannot find any correlation between coverage and reward, we think that neuron coverage is not a sufficient metric to reach substantial conclusions about DRL networks. Thank you everyone for your time and your attention.